Hey guys, we want to talk about integrated rate laws. We want to summarize our kinetic relationships in this one. All right, so first, the reaction order, all right, and the reaction rate must be determined by experiment, all right, the method of initial rates. Okay, what does that mean? So the rate of the reaction, all right, rate is going to equal some rate constant K. All right, that's my rate constant K. That's got to be determined by experiment with whatever the concentration of our reactant, whether it's A, whether it's R, right? And your order, right, is the number up here. That's your reaction order. So the reaction order, right, is that, right? That's our reaction order, and the rate, right, is determined experimentally, and so is the rate constant, K. It's all determined by experiment. The rate law, which this is our rate law, relates the rate to concentration. The integrated rate law, right, which we integrate, we mathematically derive, relates concentration of the reactants to time. All right. And we're going to go through those. And there's half-lives, right? Half, where you have the time it takes for the concentration to fall to half its original amount. And first order's time, or independent of concentration, zero order, and second order are dependent on the concentration. So let's talk about first order first. First order. And so we have our first order relationships, the natural log concentration of our reactant, any reactant A at time t, over our concentration of A at time 0. All right, and that's all, remember, that's all in the natural log, equals negative KT. Or the concentration of A at time t equals the concentration of A at time 0, e to the negative KT, right? And then T1/2 for this first order reaction is the natural log of 2 over the rate constant. Now, graphically, to help determine this, oh, that wasn't an arrow. Two graphs here. One, and we're cheat. Two. All right, we're actually going to do all three of these, so I'm going to cheat on you guys. Technologies can be wonderful. We'll do it about there, and we'll do it about there. Perfect. All right, so now if we graph, all right, if we're going to graph the concentration of A time T versus T, it's going to look something like this first order. First order looks something like that. That's the integrated rate law we kind of showed you previously. Now, if we graph for first order, all right, first order, it's the natural log of A, concentration of A at time T. If we graph that, it becomes a straight line, right? And this is T. The slope is K. So the slope of this line is our rate constant, which is neat. It's actually negative K. Let me get more space in there. Right, and that makes sense. The slope's going down, right? And then this y-intercept right here. Y-intercept is the natural log, oh, I put an H down, sorry. The natural log of our original concentration of A. All right. So if you were graphing, rate data, and you take concentration of A and time, and you get this kind of, it's a better curve than what I drew, but if you get this nice curve here, right? Okay, and then you graph the natural log of concentration A and time, and you're going to get a straight line. That's good. That's what we want. Like, okay, I know we got first order. Second order. right? And so our second order reactions, right, we got 1 over the concentration of A at time t equals kT plus 1 over the original concentration of A, right? And then T1/2 is going to be equal to 1 over your rate constant times your original concentration, right? So that means our half-life is concentration dependent now. And as A, right, as this concentration down here for A, as that number gets smaller, right, as that number gets smaller, what happens to T, right? All right, so if you go think about it, you got 1 over 100, right, versus 1 over 50. Well, 1 over 50 is bigger than 1 over 100, right? So each half-life is longer for second order. Now, if we graph these things, again, right, if I graph the concentration at A with T, you're going to get the same type of curve. But when we do our other graph, if I do 1 over the concentration at A at time t and t, I'm going to get a straight line like this. All right? And the slope is k, and the y-intercept is 1 over the original concentration. So there's second order. And finally, third order, or zero order. Sorry, not third order. You could do third order if you did calculus, but we don't do that. So we got zero order. Right? And zero order, we have, let's do green. Right? We have 1 over, not 1 over, sorry. You have the concentration of A at time t equals negative KT plus the original concentration. And T1/2 equal to concentration at A times 0 all over 2K. And so with this half-life, if I have 100 here over 2K versus 50 over 2K, right? Each half-life is faster, right? Twice as fast. Okay? And so if we do our graph here, all right? Okay? If we do the graph, it's still going to go concentration A at T, T. However, this graph for zero order, it's just a straight up concentration. No, I'm sorry, I did this wrong. If we do this graph, you're going to just get R versus T. All right? Just like that. And your slope is negative K. And your intercept is your original concentration. There you go. Now, last thing. First order, right? First order, rate. Rate equals K times A to the first order. Second order, rate equals K A squared. Zero order, rate equals K. Why? Because the concentration of A is to the zero, which is gone, right? We don't need that. It's just K. So that is the summary of our kinetics that we do in Chem 2 here. All right. And so those are your orders. If you needed to graph something, what's the graph going to look like? Well, that's approximately what the graphs are going to look like. Okay. And so if you just graph concentration, the concentration at A at time t with t, if you do that in Excel and you get the straight line, you got zero order. Otherwise, you're going to you're going to exponential line, so you're going to have to either try the natural log or 1 over, which in Excel it's very easy to do because you can do that math quite quick. All right, so hopefully that makes sense on the summary, and we'll see you in the next video, guys. Take care.